Our jaws were on the ground. We had to lift them off the ground every single iteration of the model output.
Now we seem to start off a warm spell, let's say in the mid-20s, and jump straight to 30 within a day or two, no trouble at all. Now we'd get mid-30s quite often, almost something like every other year, whereas 30 years ago it'd be a once-in-a-decade experience or even less.
The frequency of blocking is projected to decrease over Europe in the future. But the strength of the relationship between the blocking and the heat waves increases.
So it's non-linear, it's exponential, and when you're at the extremes of climate, it's what we're talking about here, that's when that actually matters quite a lot.
As a meteorologist and weather presenter, I've noticed more and more temperature records being broken in recent years, and not by small margins either. Records that stood for decades are now being broken by 1, 2, sometimes more than 3 degrees. One term that's often used to describe these extraordinary heat waves is heat dome. But what exactly is a heat dome? How does it produce such extreme temperatures? And are these events becoming more common? To explore those questions, let's start by looking back at Western Canada in the summer of 2021 and the heat wave that brought the term heat dome into headlines around the world. In fact, this was an event so extreme that the meteorologists forecasting it struggled to believe what they were seeing.
Our jaws were on the ground. We had to lift them off the ground every single iteration of the model output. You know, every 6 hours, you could see another version of more and more coalescence of these values that we couldn't believe our eyes.
Today, Armel Castellan is an extreme heat services technical advisor at the World Meteorological Organization. But in the summer of 2021, he was one of the meteorologists warning Canadians about a heat wave so extreme that it shattered the country's temperature records and stunned forecasters across North America.
I would say that we were confident that we were going to see temperatures that were going to hit the upper 40s, maybe 48, maybe 48.5, which was already 3.5 degrees above the previous national record of 45 degrees. So when the first locations started to see those temperatures above the national record, and it wasn't just Lytton. Lytton got, of course, its place in infamy because it broke the record, and it was the highest temperature we saw at 49.6 degrees Celsius. But Kamloops and Kelowna, which are much bigger centers, also in the Okanagan Valley, dealing with this heat as well. It was, you know, usually you see one location break a provincial or a national record. You would expect it to be by 1/10 of a degree. Then to see it be obliterated day after day. In fact, I remember the media getting on board with kind of a Canadian hockey analogy, because when you score 3 goals, you score a hat trick. And so that sports analogy permeated into the headline, saying like, this is a hat trick of national records being broken.
As the event unfolded, a phrase began appearing in headlines around the world: heat dome. It became the defining description of this extraordinary heat wave. In simple terms, a heat dome happens when a large area of high pressure becomes stuck over a region. Air sinks, warms and dries, skies stay clear, the ground heats up, soils dry out, and that allows more of the sun's energy to go into heating the ground than evaporating moisture. Therefore, the pattern keeps recycling and amplifying the heat. Because warm air expands and occupies a deeper layer of the atmosphere than cooler air, it can appear as a dome of heat that's difficult to shift. Here at the Met Office, we don't tend to use the term heat dome, preferring instead to talk about persistent summer blocking highs. Whatever they're called, these weather patterns not only bring unusual temperatures, but profound consequences for the people caught beneath them.
This house I lived in had no business being in anything close to 40 degrees. I was sweating through my shirts. I was having to change shirts every couple interviews. And we put up the tent outside. I mean, again, extremely fortunate to have a little backyard, put up the tent and sleep outside so that we didn't have to deal with this delayed cool down in the indoor environment. People were sleeping on their little decks. You know, some people have apartments, they have a small deck, and that was where they were kind of finding that respite in the overnight period in order to kind of make it through these several days. But we know that others were not coping super well. One of the big revelations of the heat dome of 2021 in June in British Columbia was that certain vulnerable populations were disproportionately affected. It was destabilizing. It was hard to believe that this was happening. And, just a couple days after peak heat, and as we're dealing with what I understand now is kind of like peak mortality, because it always has a little bit of a lag before you're really succumbing to the heat, where your indoor environments are creeping up. It's not just an outdoor event, it is absolutely an indoor event, because that's where we live. We don't live in the tropics. We live inside our houses most of the time. We work inside of buildings, and people were cooking, with temperatures upwards of 30 degrees, 35 degrees inside their homes, but not just for a couple hours in the afternoon, but overnight. So we learned a lot from this event. We were shaken from this event also to learn that we lost over 600, and in some cases, or some analysis, over 700 people died as a direct result of this heat in British Columbia alone.
We're filming this video in June 2026, and of course we've just experienced our own extraordinary May heat wave. What struck me speaking to Armel were the meteorological similarities between what Canada experienced in 2021 and what we've just had in the UK. So I've come here to the Operations Centre in the Met Office to speak to Paul Gunderson, and we're going to chat to him about what causes such extreme summer heat in the UK. Paul Gunderson is a principal operational meteorologist at the Met Office with decades of experience. I started off by asking Paul about what ingredients need to come together in the atmosphere to cause the UK's most extreme heat waves.
Well, the way that we get high temperatures in the summer comes from a number of components, and quite often you'll see it being described very simplistically as hot air wafting up from Spain or the continent. It's rarely as simple as that. There are three main ingredients. One is dynamical, so we have a large blocking high through the depth of the atmosphere. We have subsidence, we have sinking air, and through a process called adiabatic compression, which means that the rise in temperature is forced by a change in pressure, no external heat's coming into the system. We build this sort of potential heat within the atmosphere, which then, when we then link that in with solar insolation, which this time of the year is a net positive, which means you have more coming in through the daytime than escapes out radiatively overnight. That build-up allows us to realise that inherent warmth in an air mass, which builds up over a number of days. On top of that, we can also have something called warm advection, which is the first term I kind of reference, where hot air can be drawn up from a hot source like the continent, Iberia, and often the extremes which occur in the UK, like 2022, will come through a combination of all those factors as coming together for some period of time.
And we had the initial setup in which it was relatively dry, wasn't it, for a while through spring, so there was less evaporation, less of that solar energy was going in to evaporate the water from the soils, and it allowed for more efficient temperature build-up each day.
That's right. So even though the first half of May was actually quite cool, relatively cool compared to old climate, let alone current climate, it was still relatively dry, and the spring as a whole across England and Wales have been quite dry as well, much like the previous year actually. So yes, as you say, the soil's dry, so far less of the solar insulation is being used up to evaporate moisture out of the soil. It's going straight into heating the ground, which then of course heats the air.
Remember, we went from talking about overnight frosts in some places the week before, and then suddenly talking about the May temperature record being broken, not just by a fraction of a degree, but by, in the end, 2.3 degrees. Were you surprised by how much that temperature record was broken and how quickly, or is this something you've come to expect in the modern climate?
I mean, first of all, while changes in temperature are common to spring and always have been, we can get frost one week and a heat wave the next. That's not unusual. This was an exceptional heat wave by a margin of 2 degrees, beating old, long-standing records. Weren't surprised or shocked because the modelling's pretty good these days and we could see it coming a number of days out. I think from someone looking forward to this 20 or 30 years ago might not have believed you could break a record by that margin, but obviously we did do. And it's not just here, but across parts of Europe and North American continent in the last 5 years, we've seen other similar records go by some very large margin, which is very unusual when you're at the very edge of climatology.
Yeah, each summer we're we seem to be talking about these records being obliterated, not just in the UK, but all around Europe and North America and so on. Have you got a sense from being a meteorologist for many years that these records are now being broken much more quickly and much more large margins?
It very much feels like, you look back at hot spells in the 1990s or the early 2000s, it would take a longer period of time to build up to the sorts of temperatures we now get to very, very quickly. So a 1990s anticyclonic spell might have started off with temperatures of 21 or 22 in sunshine, and then after a couple of days it's mid-20s, then high 20s, and you might culminate a 7 or 10 day hot spell with 30 degrees perhaps, and maybe 32 in London and the southeast, and that would be the hottest day of the year, and that would be a big deal. Now we seem to start off a warm spell, let's say in the mid-20s, and jump straight to 30 within a day or two, no trouble at all. And now we'd get mid-30s quite often, almost something like every other year, whereas 30 years ago it'd be a once-in-a-decade experience or even less. So the fact we get to extremes much more quickly and then beat them by a greater margin is what's now clearly a part of climate change, because the background warming has allowed the margins to shift and the tails of climate to be stretched ever further to the right than they were before.
Do you think we're seeing changes in the jet stream in the summer, more blocking highs, or just simply when it's warm, it's warmer than it used to be?
I don't think it's clear cut that we're seeing more blocking highs, but I think when we do get that sort of synoptic pattern which supports hot weather, the background climate is allowing us to reach those temperatures much more quickly and in a much more extreme sense as well. We can build up to 30 degrees very, very quickly and exceed it over a wide part of the country when that would have once upon a time been the hottest day of the year. Now it just simply isn't.
Paul's explanation helps us understand how extreme heat happens in the UK, but one important question remains. Clearly, temperature records in the summer are being broken more frequently and with higher margins. But what I really want to know is that down to changes in circulation, i.e. is the jet stream becoming more wavy, allowing more blocking highs to develop, more of these heat domes, or are we seeing the same weather patterns we've always seen, but when they occur, we're seeing higher temperatures simply because the whole world is warming? Scientists are still debating exactly how climate change might alter the jet stream and blocking patterns, but one Exeter University study caught my attention. Published in Nature in 2022, it explored the link between blocking highs and heat waves in a warming climate. The lead author has since left Exeter University, so I went to speak with co-author Professor Jennifer Cato.
The frequency of blocking is projected to decrease over Europe in the future, but the strength of the relationship between the blocking and the heat waves increases. So if we only had a change in blocking, we would expect to see a decrease in heat waves, but the change in that strength of relationship leads to an increase in heat waves associated with blocking, and then the background warming provides a larger increase in the heat waves that we see.
So even if we're not going to see more blocking highs in the future, we're likely to see higher temperatures when they do occur. Why do you think that is?
Yeah, so that's right. So there's an increasing relationship between the blocking and the heat waves, which seems to be associated with coupling between the land surface and the atmosphere. So a decrease in soil moisture leads to a kind of feedback effect where you get more sensible heating at the surface for the same atmospheric conditions.
There has been a lot of different types of research with conflicting results in terms of blocking high frequency or the waviness of the jet stream. Do you think we're any closer to a definitive answer?
I think there's still a lot of uncertainties. There's many different ways of defining this waviness or blocking in our data sets. The results we get in that do depend on the metric we use, the model that we look at. But I think what this research really shows is that independent of whether that we see increased jet waviness, we will see increases in heat waves. So even if we have a decrease in blocking in the future, we still expect to see increased heat waves associated with those due to the strength of the relationship and also the background warming.
So the atmosphere may not be producing more blocking highs in a simple, straightforward way, but the heat we get from them is increasing. We're going to see more and more hot extremes, aren't we, in the future?
The background warming means, and that's going to continue, of course, that the sands have shifted, so the tail distribution also shifts. And what was once, a once in 50-year extreme temperature from some period ago, a background warming of 1 degree of the climate makes it something like 4 or 5 times more likely, and then a background warming of 1.5 degree makes it about 8 times more likely. So it's non-linear, it's exponential, and when you're at the extremes of climate, it's what we're talking about here, that's when that actually matters quite a lot.
But forecasting the heat is only part of the challenge. Turning forecasts into advice and action is what saves lives.
I think the lesson really is that governments have and agencies like NGOs, ENGOs, civil society, and the general public have now figured out the obligation to coalesce around this particular hazard and its ripple effects. And so heat action plans are one element that are being developed. You know, places like India have hundreds of heat action plans for all levels of society. So it's very positive for, you know, an extremely populous nation like India and their neighbors like Bangladesh and Myanmar to exercise this kind of adaptive nature and go beyond just the forecast. The forecast is kind of, yes, here's the alarm bells, the warning is here, and it's coming in the next 4 or 5 days or so. But now you actually have a way of coalescing and building agency because you kind of know what to do. And action is what humans are so fabulous at. They coalesce around that agency and beautiful things can happen and lots of lives. Most of them are unnecessarily exposed to this heat and are absolutely preventable deaths.
So, are heat domes getting worse? The answer isn't straightforward. We don't know for certain whether summer blocking patterns will become more common or stay as they are. But we do know this: when they happen, they're occurring in a warmer climate, over drier ground, and they're capable of producing more extreme heat than they could in the past. In other words, even if our weather patterns don't change, the consequences are becoming more severe. If you've enjoyed this video, check out the Met Office YouTube channel where we publish regular forecasts, deep dives, and explainers into every aspect of the weather.